All right, so I want to go over a bunch of stuff today. So I want to talk about the homework that you just got back. So I graded number 3. And it looked like most people were on the right track, but I want to go through this in some detail and talk about some of the things to watch out for or to note. And then we're going to talk about the lab and the Verilog software and all that kind of stuff, because I switched Verilog software on you after class. So I want to run through using the Icarus tools and sort of touch base on that. And then basically want to spend the rest of the time talking about Verilog and the homework that you're working on and the lab that you're working on and such. But let me start with question 3 on the homework, and then if there's any other questions on the homework, we can talk about those, obviously. So this is chapter 7. That is not the same homework. All right, so question 3, we've got this state diagram that we talked about last week. And let's just draw a picture from this first of all. So you've got 2 states, A and B. And we have 2 inputs and 1 output. Okay? The output apparently only depends on the state. So is that what we call a mealy output or a Moore output? You got a 50% chance if you guess. It's just terminology. There's no reason why it's one or the other. So if it's only dependent on the state, that's a Moore output. Okay, I don't know how to remember that. I would put that on your note sheet. So a Moore output you can represent inside the bubble for each state. So for A, the output is a 0. For B, the output is a 1. So I would draw my states like that, right? 0 and 1 inside. And I can draw a key over here, which says state. And then underneath it, we have Z. And there's a pair of inputs, X, Y. And so our transitions are going to be labeled with the value of XY. I could do YX, it's just going to change the order of the 1s and 0s on those arrows, but you got to have a key so that you know if this arrow is labeled 1, 0, is that X equals 1, Y equals 0, or is it X equals 0, Y equals 1? So the key is telling you how to read your diagram. And now we just fill in from this table. So if we're in state A, basically we stay in state A if our input is 0, 0, or 1, 0. So I'm going to draw those diagrams. Here's a 0, 0, and here's a 1, 0. And the other inputs, 0, 1, 1, 1, are going to take us to state B. So here's... Am I doing the wrong part? Yes, this is the unsolved. So it doesn't matter for A or B. The state diagram is going to be the same. So 0, 1, and 1, 1 will take you to B. And then if you're in state B, inputs 0, 1, and 1, 1, 0, 1, and 1, 0 take you back to B. So 0, 1, 1, 0 leave you in this state. And the other inputs take you to state A. So 0, 0, and 1, 1. So there's a state diagram. And so there's two parts. There's full encoding and there's one hot encoding. So full encoding is what we've been doing so far. So let's make a table for that. Okay, the states are called A and B, but we don't want to write a truth table with A's and B's in them. We want to write a truth table with 1s and 0s and maybe dashes. So we need to have a table that maps from A, B to 1s and 0s. Okay, so for full encoding, how many flip-flops do we need? One, right? So we can just call that flip-flop Q. And it's got two possible values, 0 and 1, and we just say what does a value of 0 mean, what does a value of 1 mean. So most people said 0 is going to be state A, 1 is going to be state B. You can do it either way. So now we can make our table, which says, here's your inputs. I'm going to start this on a... Here's your inputs, X and Y. And our state, our present state, which is Q. All right, before you talk about the flip-flop inputs, you got to list the next state. Okay, even if you're doing this in your head, it's really important to make sure that you have the present state, and then you also have the next state, what we usually call Q plus. Sometimes it's Q with a star on top. But it means the next value of Q, given this present value and this pair of inputs. And this, the next stage you just fill in from your state diagram or your state table. Right, so here's the inputs X, Y, here's the present state Q. We've got 8 combinations, so 8 rows. So look at our diagram conveniently off screen. If your present state is 0, right, that's state A, and your input is 0, 0, your new state is also A. If your input is 0, 1, your new state is B. So if you're in state 0 and your input is 0, your new state's going to be 0. If you're in state 0 and your input is 0, 1, your new state's going to be B. And so on. So you fill in this whole table based on present state and inputs. And let me see if I have that. So barring typos, that turns out to be your next state. And now you can fill in what the input to your flip-flop, and it was a T flip-flop, what the input to your T flip-flop should be. And that's simply saying, do we want this flip-flop to change state to toggle or not? If you don't want it to toggle, set T to 0. If you want it to toggle, set T to 1. So there's the values on the T flip-flop. And then the output Z should just correspond to the state. If we're in state A, Z should be a 0. If we're in state B, Z should be a 1. Okay, once you get to here, once you have the flip-flop input specified and you have the outputs of the system specified, you're done with the state machine-y part of all of this, right? Now it's going through and finding an equation for T, finding an equation for Z, maybe simplifying and then sketching a circuit that sets T and Z based on X, Y, and Q. Okay, and T is always going to be a function of the inputs to the system and the present state. right? Not a function of the next state. And so z is another function of x, y, and q. So that was one thing. Make sure that you're using the present state when you write equations for t or z. Make sure you use the right kind of flip-flop. Okay, so that's the full encoding one. The one-hot encoding, basically the same process, except number one, your state table is a little different. So one-hot encoding, 2 states, 2 flip-flops. So your flip-flops might be Q1 and Q0. And your state and this doesn't say anything about illegal states, I don't believe. So one-hot encoding, right, the idea is this would represent one state 0, 1, 1, 0 would represent another state. So we might just say this is state A and this is state B. And these other possibilities where both of your flip-flops are the same, we're going to consider those don't cares. We're just going to say those are not states that we're ever going to see, so we don't care what happens in those states. So now your input table which used to list x and y in a present state, now it's got 4 variables. So you've got an x and a y, those are your inputs, and you have your present state, which is Q1, Q0. Should have brought my rubber stamp. So you got 16 rows in your truth table. And so for each of these you list your next state. Well, if my present state variables are 0, 0, that's a state that I don't care about. And so I don't really care what the next state is, so I can just mark these as dashes. And similarly, if my present state is 1, 1, I don't care about that state. I don't care what the next state is. And so all of these states that don't match A or B, we can just put don't cares for the next state. But for these other values, for example, if you're in state 0, 1, that's state A, and your input is 0, 0, you should stay in state A, which means your output should be 0, 1. If you're in state B, which is a 1, 0, and your input is 0, 0, your new state should be A, which is a 0, 1. So it can be helpful to write down what the state name is along with the coding of the flip-flops that correspond to that. I'm kind of skipping that step here. But we've done that in the past where we had inputs and then the name of the state and then the values of the flip-flops that correspond to it and so on. But this is what you're after, right? The set of next states corresponding to your present state. And now you got T flip-flops. So here's flip-flop inputs. So this is T1 and T0. And this gets filled in just like in the past problem. You look at Q0, it was a 0, we don't care what the new value is. That's a don't care. Next row, Q1 is a 0, and we want it to remain a 0, so we do not toggle. Here it was a 1, and we want it to become a 0, so we do toggle. And here it was a 1, and we don't care what the new value is, so that's a don't care, and so on. So you write these out, T1 and T0, you make a K-map, maybe simplify it, write down equations, and you can use that to build your circuit. And your output, Z, so we don't really care what it is here. State A, we want it to be a 0. State B, we want it to be a 1, and here we don't care. And that pattern's going to repeat. So Z is going to end up being, you can just set it equal to Q1. And most people did that. So things to note about this, right? If you include the don't cares, you make your circuit easier. If you don't include the don't cares, you still get a functioning circuit that works perfectly. But if you're trying to come up with a circuit diagram or equations, it's easier if you have more don't cares. So make sure you list a state table, and I usually found this somewhere in the homework, but it was usually sort of buried in amongst other stuff. Or instead of saying 0, 1, I saw people writing in A, B, A, B. And if you know you want to go from an A to a B, right, well, for a T flip-flop, that's pretty easy. It's toggling. But if it's a different kind of flip-flop, you got to go back and you got to look at a table and see, okay, we want it to be a 1 or a 0 and so on. So these tables stick to 0s and 1s, right, and make a mapping table somewhere that says what is state A, what is state B. Other than that, this looked great. So most of the large deductions on the homework were, so a bunch of people didn't turn in the homework, okay, which is 0. Some people turned in the homework, but they only did 2 or 3 or 4 questions, right? And this was a huge homework assignment, right? I mean, you can easily do 15, 20 pages without wasting space, because there's a lot of circuits to work on, right? So if you didn't do any of the questions right and you didn't do question 3, that's a pretty low grade. A lot of people did question 3A but not B. Some people did 3B but not A. So that cost some points also. If you did 3A and 3B, you probably got a pretty good score. So, and like I say, it's a large assignment, so if you left it till late, you might have run out of time and such. But if you didn't do all of the problems, I strongly recommend doing them, right? Because the only way you get good at doing this kind of synthesis is just practicing it. And there'll definitely be a state machine synthesis question on the final. So ideally you get some practice beforehand so that you can be fairly efficient at it. So any questions on that or any of the other homework questions?
Why is Z identical to Q1?
So this was the full one-hot encoding that I came up with, and your Z output should be 1 if you're in state B and 0 if you're in state A, right? So for me, state A was coded as 0, 1. So it's this row right here, Z should be a 0. Right here, Z should be a 1. Right? Now if you coded A and B differently, it might end up being the complement of Q1.
Okay.
Right? But then if these are don't cares, it turns out this always matches. Q1. Right. So it's just kind of a happy coincidence. Other questions? Okay, let's give test code to play with. All right, so So is anybody who has not gotten Icarus either downloaded or run it on the Collaboratorium PCs or anything like that? Raise your hand if you have gotten something done with Icarus. Okay. So I posted a new Lab 7, and it's basically the same questions from the old Lab 7. But a different set of software. So I tried the Xilinx software that's currently available for download on the Collaboratorium machines, and it gets into all kinds of complaints about VirtualBox, and so you have to download and update VirtualBox and stuff like that, and it's going to end up being about an hour worth of installation every time that you go in there to do Verilog, and even then I don't know if it's going to work, because when we did this last year I spent a few weeks sort of nailing down like the exact steps and all the edge cases and things like that. I silly me assumed that it was still going to work this year. The software is not even installed on the machines right now. So I tried reinstalling last year's software, and that doesn't work anymore because Windows has updated. So, so Icarus Verilog is an open source effort to be able to run Verilog compilation, simulation, waveform analysis from a command line in a variety of environments.
So we have the Spartan chips, right?
Mm-hmm.
Would you be able to do the extra credit lab then?
No, so the problem is that we can't program chips using Icarus.
Could we program it with Icarus and then give it to you guys, and then you guys use stuff? Because I think you have Xilinx servers on your laptop. Right?
Yeah, so if you're interested in doing an extra credit lab, we can make it work, right? We can get a setup which works, and have you go from there. All right, so this is written from a Windows-centric viewpoint, but Icarus actually runs natively on Linux. So if you go to there we go, iverilogicarus.com. If you go to here, it tells you how to download and install on Linux, and it works very well under Linux. But it seems to work well under Windows. It's just this weird site, blire.org. And if you do this on the PC, you got to delete the old setup of Verilog, because that doesn't work anymore either. It gives you an unknown error when you try to run it. And if that old installation is sitting there, installing the new one doesn't actually overwrite the parts that are failing. So go into a folder and delete the iVerilog folder, and then go ahead and download that and do the install. And Windows, you got to do window key CMD to open up a DOS window, and that's where you run this from, because they don't have like a console thing, I guess. So DOS is always there. So go into a DOS shell and just do c::iVerilog. That basically gets you to the compiler. All right, so so experiment 1 takes you through step by step how to exactly compile and simulate, and then look at waveforms for a Verilog module. So there's no writing Verilog for experiment 1, right? All the code's given to you. Cut and paste doesn't seem to work very well for some reason, from PDFs to plain files in Windows. At least when I tried it, it was giving me weird characters, so you may have to type this in or cut and paste it and edit it up. So this first quotation mark, this is a back quote, not a single quote. So it's the quote that's next to usually the tilde key. Everything else is pretty self-explanatory, but Verilog is really picky about syntax, so if you miss a semicolon, right, things will happen. So this is just an example of an AND gate in Verilog. We've already talked about the assign statement. So this creates a Verilog module for implementing an AND gate called experiment 1. takes two inputs A, B, produces their AND on X. Windows comes with Notepad, which is their editor, but it's kind of pretty primitive. If you want a slightly better editor, or actually a much better editor, you can download and install Notepad++, right? And if you download it and put the installation file on your flash drive, it's really quick to install. And that will, you know, do syntax highlighting and count line numbers for you and stuff like that. So that can help. Usually if you're forced to use a Windows system, it's nice to have a flash drive with your favorite tools on it that you can either run from the flash drive or install pretty easily. So you can throw the Icarus Verilog installation files on a flash drive, Notepad++. You can save your work there because when you log out of these machines, all your work gets deleted. So, you know, make yourself an environment that works for you, and you can run from that.
So for Notepad++, how do we run it from the command line? Would it be Notepad++ exp1.b?
I think so, or you can just open up Notepad++ from the regular, you know, point and click, and then in there you can say file open and put in the name. But I think it's actually Notepad with 2 plus signs after. It might actually be on the path. I don't know. All right, so we did talk a little about test benches before when we were looking at the other software, right? So the test bench is a thing that you run that actually stimulates the inputs. So here's a sample test bench that will test our AND gate. And so the parts of this that are unique, there's this display statement. I can say $display, and I can put in messages, right, which will appear while I simulate this. How many people here have taken CSE 121? Okay, so if you've done 121, you know about printf statements. This works like a printf statement. So if I say display, I can put something in quotation marks. If I have a %d in here, it expects me to list the name of some variable after that string, and this first %d gets replaced with the value of in1. This %d gets replaced with the value of in2, this gets replaced with the value of out. So it lets you display the values of variables while your code is running, your circuit. So display is just for debugging mostly. It lets you see what's going on. So somewhere in the beginning you also need to say dump file, and you need to name a file where it's going to write all the information about the simulation as it proceeds. And you also need to say dump vars, which says take all the variables that we're using in this circuit and write them out to whatever file I named in dump file. Okay, that just goes up in the beginning somewhere after your initial begin, and it sets things up so you can use the simulator in waveform viewer. So here we were just setting both inputs to 0. The number sign says wait this many nanoseconds, so wait 10 nanoseconds. And then I want to display the value of my 2 inputs and the output, right, which should be a 0. Then I set input 1 to a 1, wait 10 nanoseconds, and again display the inputs and the output. Set in2 to a 1 and redo that display, and then change in1 to a 0 and do the display. And then $finish just says I'm done. It closes out the files and such. So I've basically gone through all 4 combinations of input 1 and input 2 being 1 or 0, and in each case I wrote out a line showing me what the output is. Let me see if I happen to have this code somewhere. I do not. So let's write this. Oh, maybe I do. All right, so there's my test bed or test bench, instantiates my AND gate, dump file, dump vars. I don't have a clock, so I'll say hello, set my inputs to 0, print out the inputs and the outputs, and so on and so forth. And my AND gate just looks like that. Okay, so you write this code using Notepad++, or if you like VI, there's VIs that run under Windows. You can download those and run them from a flash drive. Alright, so there's my experiment1.v Verilog, so let's compile it, and let me be consistent. It doesn't really matter what you call the output. But let's be consistent. Experiment1.out. So iVerilog is the compiler, x1.v is the program I'm trying to compile, and then -o says call the output, and experiment1.out is what it's going to call the output. So if it doesn't say anything, you're good to go. Okay. If you forget a semicolon somewhere, right, then it says syntax error, malformed statement. And this 32 right here, this is a line number. Okay, so that's the name of the file, experiment1.v, and this is saying you line 32 there was a syntax, line 33 there was a malformed error. Somewhere around there is probably where the mistake is, but occasionally it's like 10 lines before. Okay, it could be something weird, but start looking around there, and if you see multiple errors, pick the first error that you see. Figure out what that is, fix it, recompile. If you have 10 errors here, don't ever start working on all of those errors until you recompile after fixing the first one. Because a lot of times fixing one error will make all the other errors go away. Okay, so you can do 32 Shift G if you're in VI to jump down to line 32, and you can do Control G to see what line you're at. And if you're in Notepad++, there's line numbers on the side. So somewhere around here is a syntax error, right? And it's actually on the previous line, there's a missing semicolon. Okay, it doesn't go crazy if you get multiple errors. Alright, so compile it up, everything works fine. And there's my experiment1.out that was just created. And if I look inside that file, there's all kinds of things I don't really want to see. Okay, this is all like internal information that the software uses to understand what my Verilog is supposed to do. Okay, but you never want to like try to edit this file. Alright, so that compiles it. Next we need to simulate. So to simulate we use the command vvp, and it's just vvp in the name of the output file that you created. So vvp exp1.out, and it goes ahead and it runs it. So it tells me it's dumping into test1.vcd. There's where I said display hello, and there's my 4 display statements that show me the values of my inputs and my outputs. And here the inputs are 0, 0, x is 0, 1, 0, x is 0, 0, 1, x is 0, and this third line, input 1 and 2 are both 1, and the output x is 1. I got an AND gate, right? So that tells you that your Verilog is doing what it's supposed to do. So if you're doing the homework and you're actually writing the Verilog and compiling it and testing it with the simulator, right? For the homework, I don't ask for, do I ask for traces and waveforms and all that? No, I just want a Verilog code, right? So if you want to know if your code is working, right, this is enough. Do whatever you need to do to convince yourself that the Verilog code is correct, and you can turn in the code like that. For the lab, I also want to see waveforms and things like that. So our third and final tool is Gtk Wave. And so Gtk Wave, you basically put in the name of your VCD file, right? The thing that was specified in the dump statement. So test1.vcd. Should have called it experiment1.vcd, but Gtk Wave, test1.vcd. And it brings up a little splash screen, and then you get this kind of window. And so over here in the upper left, you should see the name of your test bench. If you click on that, you get a set of signals here, in one, in two, and out. Drag those over to this middle window, one at a time. And what we're seeing are the waveform values for those inputs and that output. Now this is picoseconds going across the top. Got 1,000 of those for a nanosecond. We've got a bunch of nanoseconds to wait in the beginning. So if I start scrolling, I'm going to be here a really long time. Okay, so you can control scroll wheel to zoom out or zoom in. But you can also hit this little box with 4 arrows pointing in. It's called zoom fit. Just click that and it makes everything visible. And here's our waveform. First 10 nanoseconds we hadn't set up any inputs, so they're listed as red, which means undefined. But then at 10 nanoseconds, input A and B were 0 and the output was 0. Here's where input 1 raised to a 1 and the output was still 0. Here's where both inputs were 1 and the output was 1. Here's where the inputs were 0, 1 and the output was 0. So that's a good timing diagram. If you view, you can say use black and white, and that's possibly a little harder to read. It's actually impossible to read, but it's easier to print. But there's all kinds of things you can do, right? We can insert a blank line. Well, it doesn't really help. That's pretty horrible. I'll just go back to color. There's options you can play with. You can change the height and the font and things like that. You can set the colors and so on. So you might be able to make it easier if you want to like make printouts or something. But that's the basic idea. Okay, that's the whole kind of tool chain. So edit your Verilog code somewhere, right? Notepad, VI, whatever. Compile it with iVerilog. Simulate it with a VVP. Look at the waveforms with Gtk Wave. And it's a process, right? You simulate it and the values don't look right, so you go back in and you edit it again. And you say, oh, I really wanted an OR gate. So there's my OR gate. So do the Verilog, do the VVP. Well, now you can see it's outputting a 1 when any input is 1. Redo Gtk Wave. Blow this up, click on that, drag your signals over. Zoom to fit. There's my OR wave timing diagram. So rapid prototyping is like key, right? When you're trying to work on a project, you don't want to have to spend most of your time fighting with the tools or you know, trying to understand what a message means or something. You want to spend your time working on the thing that you're working on, right? The creativity that you're bringing to the problem, whether that's writing code or, you know, designing circuits in Verilog or whatever. So it's worth finding a tool chain that works efficiently for you and getting really comfortable with it. And that's part of the purpose of the homework questions. So if you find yourself compiling your code 100 times, that's not a bad thing. Right? It's a feature. All right, so questions about the mechanics of using the compiler, things like that. So they want to spend the rest of the time actually talking about Verilog more and digging into things like register and all of that stuff.
I have a kind of a question at the
Yeah.
very beginning. You have like the
Time scale?
Time scale, yeah.
Yeah.
What is that?
I don't actually know, to be honest. The 1 nanosecond,
Do you have to have it?
well, as I used to like telling my students, let's find out. So it compiled and it simulated and it ran,
It seems like it doesn't zoom you in right away.
but over here it looks like 30 seconds and over here is 90 seconds. So this simulated a minute and a half worth of execution. Okay, maybe that's good enough, but right, if this was a complex circuit, maybe I need to know what's going on at a smaller time scale. So the 1 nanosecond, I believe, is, well, I don't know. I can fake it. It has something to do with the resolution that's used inside the simulation. How much does it advance each moment? And I don't know what the picosecond does. If picosecond is the resolution and nanosecond is the output, or what. But it's ultimately saying what's the size of a time step. Because simulations, these things in reality, for the most part, time is continuous. At a quantum level, it's not. But mostly it's continuous, right? Time flows smoothly. But when you're simulating something, we can't simulate every instant in time because there's an infinite number of moments from here to a minute from now, right? So when we do simulations, we break time into these little chunks. We quantify it. We quantize it. And so you need to tell the simulator what size chunk should you break time into. If you do calculus, this is what dt is, right? dt is supposed to be 0, but when we actually do calculus on a computer, we use a delta t, which is very small but bigger than 0. So same thing in simulation. All right, other questions? Yeah.
You said you had to drag each of the 3 inputs and then the X input on the Gtk wave individually. If you don't, will it produce something a little different? Will it even let you?
So this is really just kind of showing what's already in the simulation file, right? So if I just drag input 1 over here, right, I can see that waveform, but
You just said do one at a time. Can you select all 3? Will it
possibly.
Oh, no, it doesn't let you.
Yeah, it doesn't let you.
Okay, that's what I was about.
Yeah, the Xilinx tools you can, and the Xilinx tools you can also just double click. But yeah, this one it seems like you have to actually drag it. But you can do other things like rearrange them, stuff like that. All right, let's do a 5-minute break, and then let's spend the second half just playing with Verilog. Because there's a lot to say about that.